Welcome to Lecture 8A, entitled Small Signaling Modeling Framework. The material for this lecture comes from Reading Assignment 2, the Introduction, and Section 3.1. And the objectives of this teaching module are to introduce the framework for determining the time evolution of a dynamic system consisting of state variables, inputs and outputs for small perturbations or changes about a DC, or we call sometimes equilibrium operating point. So the concepts and definitions contained within this teaching module include the Jacobian matrix, which is something that's going to be new to you. So we'll spend a little bit of time just describing it sort of at a high level. Later on in the course, we'll be looking at it in more detail for different situations. Secondly are the system equations comprised of state space equations and output equations. And then if we consider these equations, then there's three types of variables to consider: state variables, input variables, and output variables. And then we're going to be using the three words interchangeably: an equilibrium point or points, depending on the number of variables, steady state points, or DC operating points, essentially mean the same thing. And then finally, what do we mean by small signal equations? As usual, the second page is just a summary of contents of this lecture. I'm just mentioning here, though, that what we will do is go through all the details first, but then give a very brief example as to where this small signal modeling concept basically plays a role, in particular in relationship to what you'll be learning in ECE 231 next term. And so once we have the background information, I think you'll appreciate in terms of how useful this type of mathematical tool is. All right, so first thing is to start with what we basically define as the Jacobian matrix. And essentially what it does is it relates the partial derivatives of the old variables with respect to new variables. And I've given three examples here, each one being of a higher dimension. So this, for instance, would say, if you're saying that x is defined in terms of a new variable, then the partial derivative of x with respect to u, or fu, is what we're going to call basically Jacobian matrix. But the matrix in this case is 1 by 1, in which case we just say it's a scalar. So no need to actually make use of the word matrix in this context. It's only when you go, say, to two variables that suddenly we end up with a matrix. So for example, for two variables, we could say x is a function of uv and y is a function of uv. If we then order a matrix with a 2 by 2 matrix with elements, first row involving partial derivatives with respect to f and the second partial derivative with respect to of g, then we end up with this 2 by 2 matrix. And this we call the Jacobian matrix, and this is with respect to the variables u and v. Sometimes we use this shorthand notation instead of basically having to write this all out as in this form. We can now move on to, say, a three variable system, in which case x is a function of three new variables, so is y, so is z. In this case, the Jacobian matrix will be a 3 by 3 matrix. The first row will be the partial derivatives of f with respect to the new variables u, v, w. Similarly, the second row will be for g, and the third row would be for h. So you can see there's a certain order, top to bottom, top to bottom. In shorthand form, we sometimes write it in this form. So this is just a definition. This is a starting point. Its relevance, basically, is something we'll talk about next. All right, so what are the types of problems in which Jacobian matrices appear? And so one of the examples is solving nonlinear equations, and this can be found in more detail in Section 1 of Reading Assignment 2. You are not responsible for this material, so some of this is just to give you a sort of a flavor of what's in these notes. You won't be tested on this. So this is something that's just for you, for your interest. So in what context do we use the Jacobian matrix J when we're solving nonlinear equations? Well, it's used in a recursive algorithm to compute the solution or solutions to a multivariable nonlinear set of equations. And this basically is called a multivariable Newton-Raphson method. For example, consider two implicit nonlinear equations. There's a function of two variables, and what we're trying to basically determine is what the roots of this equation are. So to solve for the variables x1 and x2, we need to solve the equation recursive until the difference between the calculated new solution and the old solution is vanishingly small. So if I've written it out in this form where x basically is just in the form of a column vector with the two unknown variables, x1 and x2. x0 basically is your guess as to what the roots should be, x1, 0, x2, 0. J minus 1 is just the inverse of the Jacobian matrix, and f of x0 basically is just the solution of these two equations at the guess values for x1 and x2. And so here, of course, you can see it has partial derivatives in it, and therefore we call it a Jacobian matrix. We need to take the inverse of this. And then what we do is, at every step, we basically take the value of x1, 0, x2, 0 that we've computed. We now basically compute a new Jacobian matrix. We compute a new value of fx0, and basically redo this computation and come up with a new value of x. This x would be this new x1, x2. We then take this x1, x2 and make it equal to x1 naught, x2 naught, and substitute back in, redo the calculation, and come up with a new x. We do that until the difference between x and x naught becomes vanishingly small. All right, so this is basically what we call the multivariable Newton-Raphson method. The other thing we use it for is small signal modeling, and this is essentially the topic that we're dealing with in this lecture. And this comes from section 2 of reading assignment 2, short. The short assignments are the ones that you're responsible for. And so what we're going to end up with are Jacobian matrices JF, BF, JG, BG, all subscripted, and they're used to relate small signals to each other. The equations take on the following form. So what you have here is a differential equation with respect to the small signals, variable x1 and variable x2, and they are related to variables x1, x2, and u1, u2. These are small signals for input variables, small signals for internal or state variables, and we have a matrix relationship basically between this vector and basically everything on the right-hand side. Similarly, we have output equations, and so these are related to the state variables and input variables through these matrices, which will be called the Jacobian matrices. Again, just I mentioned here, it's highlighted in orange, that this is the material that you'll be responsible for. All right, so let's type of problems in which Jacobian matrices appear. Let's keep on going. So this is a transformation of variables for multivariable integrations when they also appear. This comes from section 3 of reading assignment 2. This is the longer version reading assignment 2. You're not responsible for it, but I thought I'd put this in here to give you sort of an expanded view of why Jacobian matrices are important. All right, and so a key point here is that the determinant of a square Jacobian matrix, I'm just going to show it in this form, is used to determine the scaling factor when transforming a differential length, area, or volume element from Cartesian coordinates into another coordinate system. We'll find that when we do integrations, sometimes it's not convenient to use Cartesian coordinates. It's better to use some other coordinate system. And in the process of doing all the conversions, we end up with this scaling factor, which we refer to as the determinant of the Jacobian matrix. So let's take a look at some examples here. The transformations, this is one variable. X is f of u. You've used this last year when you're, for instance, doing integrations and you want to do a change of variables, and you end up having to take the derivative of f with respect to u. It's a 1-by-1 matrix, which is nothing more than a scalar. But let's move to the notion of two variables. In this case, we're defining x in terms of two new variables, y in terms of two new variables. All right, and then we compute a Jacobian matrix. And what is this used for? It's used to map an area in the UV plane, because these are two new variables, to an area in the XY plane. We'll be discussing this more in subsequent lectures to follow. We could also, for instance, take this as an example. You have x as a function of uv, y as a function of uv, and z as a function of uv, but z is related to x and y. So effectively what we're looking at here would be a surface. And so what we'd like to do is to look at how do we visualize a curved surface and relate it, say, to a 2D surface, particularly when we're looking at calculating things such as the surface area of a curved surface. Well, in this case, it turns out that we end up with a Jacobian matrix which has three unit vectors. You have the partial derivatives and the partial derivatives. Well, this is still a Jacobian matrix because it involves partial derivatives. But the determinant of this, because this involves vector elements, becomes a vector. And this is basically telling us that this is an oriented area. So even though this is related to an area, it's an oriented area, which means it depends on position. Anyway, this will be discussed later in the course when we talk about computing the surface area of curved surfaces. Thirdly, if we have, for instance, 3 variables, and each one of these is a function of 3 new variables, this is used to map a volume in the UVW 3D space to a volume in the XYZ 3D space. In this case, if we set up the partial derivatives, we end up with a 3x3 Jacobian matrix. And this is used basically to do a mapping from XYZ to UVW or the other way around. Anyway, this is the motivation regarding, why even bother about Jacobian matrices. Well, they play a very important role in many ways. And there's one last item that we'll discuss, but it's not going to be, you're not responsible for it. And that's a transformation of coordinates of vector operators. And this is section 4, reading assignment 2. Again, you're not responsible for this material. The Jacobian matrix is used in the derivation of vector operators in coordinate systems other than Cartesian. The principal vector operators discussed in this course are the gradient operator, which is this symbol that you see here, which operates on a scalar function f to produce a vector. And when you see grad f, that means basically you're creating a vector. And the vector is by taking the partial derivatives with respect to, of f with respect to x, y, and z. Those become the x, y, and z coordinates. We also will be introducing something called the divergence operator later in the course. And that involves taking this symbol with a dot product. So this operates on a vector f to produce a scalar function, and it'll have this form. We'll see later on that this is the divergence of a vector. Thirdly, we could have the curl of an operator, which is taking this operation. This is a partial, derivative operator, or nabla, with a cross product. This operates on a vector to produce a new vector, and we'll call this the curl of the vector f. Now, these things in this course are going to be dealt with in Cartesian coordinate systems, but if you were to go into new coordinate systems, you would need to do transformations to figure out what these would look like in the new coordinate system. This is where the Jacobian matrix plays a very important role. All right, so now we move to the main topic, which is basically small signal modeling. And the first thing we'll do is we'll start with what we call the system equations, which model a dynamic system. So what we have here are input variables, m input variables, k output variables, and these internal variables, n of them in this particular example, it's also called state variables, which more or less define how the system operates. This is more or less understanding the dynamics of your model. All right. So here I've just summarized what each one of these things are. Input variables, which represent the signals that excite the system, like an input voltage source or current source, if we're talking about electrical circuits. The state variables, which typically represent the internal state of a system, such as current through or voltage across an energy storage component. And y of k output variable, which is an output variable, such as current through a branch or voltage across one or more components. And nmk just represent the number of elements that we're dealing with. So if we look at a generic form of the system equations, here I'm looking at basically an example of 2 state variables and 2 input variables. Then a state variable equation would have this generic form. You can see the derivative with respect to x1 and derivative with respect to x2. This is a function of the state variables of the system and the input variables. Similarly, the x2 by dt is a function of the state variables and the input variables. Right? The output equations would take on a form like this. Output equation 1 would be functions of x1, x2, u1, u2. Similarly, output 2 in this case would be functions of x1, x2, u1, and u2. All right, just an important note, when developing state space equations to model a system, you only want one derivative to appear in each state space equation. So you've got to somehow manipulate things in such a form that it looks like this. And the output equations look like this. Then you have your starting point, and then we can do things with these equations. All right, so let's take a systems equation example. The problem statement is given the RC circuit to the right, which is this one here. We want to derive the system equations for this circuit, assuming the output variable is a power loss P in the resistor, this resistor, And the input variable is the voltage source V in T, which is this one here. This is shown as a DC, but this could be anything you would like it to make it. Just a sinusoidal, whatever the case may be. So the first step is write out a loop equation, which means you apply Kirchhoff's voltage law, and where the capacitor voltage is an internal state variable. Why is that? Because you can relate the current through the capacitor in terms of the rate of change of voltage across the capacitor. So that immediately defines this as your state variable. So always look for the differential equation to begin with, because that defines a state variable. So that's done. Second is to write the loop equation in standard state space form. So we're going to have to basically now write this out as a differential equation. And thirdly, write the output equation in terms of the state variable in the input variable. So in this case, V of C, right, we'll call X1 if we want to, is the state variable. V in T, we call U1, which is the input variable. And P in was the output variable, we'll call Y1, just to be consistent with basically the way the nomenclature we've developed so far. So let's look at step 1 and step 2, followed by step 3. So for step 1, what do we have here? The voltage across the resistor, which would be I times R, but I is C dVc by dt. So this is the voltage across the resistor, is the difference between these two voltages, which is shown here. Now, state space form means that we only have the derivative, so we have to divide through by RC on both sides, which is why we get this expression. And if you put it in sort of in the standard form, this would be function of V of C of T, function of E in T, and sure enough, that's what it is. Step 3 is basically for the output power. Well, the output power basically would be the voltage difference, voltage across the resistor squared divided by the resistance. All right, so that would be V in minus V squared over R. And so, yes, this is function of the state variable and also function input variable. So more or less, we now have set everything up so that we could move to the next step, which is really to determine the small signal model for this system. Just recall that the state variable is associated with an energy storage component. And so you'll notice V of C relates to the voltage across the capacitor. All right, so now let's move in to the modeling of the system equations and start with the linear system, but just a quick review of matrix multiplication, because with linear systems, it's sometimes more convenient to do everything in matrix form. So the 2 input, 2 state, and 2 output variable problem. So just recall, when multiplying an n by n matrix by a column vector with n entries, you obtain a new column vector with 2 entries. So you multiply row entries of matrix by column entries of the column vector. So you'll notice here, if I basically do this computation, I'm taking C1, C12, X1, X2, and multiplying this out to get this. If I take this and times this is what you see here. This is multiplying it out, you get this. So that means if I have a state space differential equation, it's linear, because linear in all its state variables, input variables, then this basically can be written in matrix form. This becomes an A matrix, and this part here becomes a B matrix. And the output equations can handle in the same way. Here they are in equation form, but actually we can rewrite these in matrix form as a C matrix and a D matrix. So this is a compact way of representing the state space differential equations and the output equations. All right, what about a nonlinear system? So here's an example of a nonlinear system. Here you'll notice that this state variable is nonlinear. It's not, it's the square. So in this case, basically, we cannot write this out in the form of a matrix equation. An output equation, you'll notice Y2 here is in terms of fourth power. So this one is a nonlinear equation. So these equations cannot be written out in a matrix form. All right, so this is something you have to be aware of. All right, this is just the general conclusion I've made here. All right, so now basically we're going to perturb the input, the state, and output variables. So what does that mean? So for instance, perturbing the input signals means you take U1t and you represent it as a steady state value, equilibrium value, or DC value, 3 interchangeable words, plus a small change with respect to time. Similarly for U2, steady state plus small change. Okay. All right. Small is typically sort of, you have to make a decision, because finally when we do a Taylor series expansion, you want to make sure that higher order terms are negligible in comparison to first order terms. So now we look at perturbed state variables and output variables. So in this case, basically, we're looking at x1 is perturbed, so this will be the steady state value of x plus a small perturbation. Similarly for x2, y1 similarly, y2 similarly. So this is the first step, basically, towards deriving a small signal model. Basically, the steady state value plus a perturbation. Okay, so substituting the perturbed signal expressions into the original differential equations and output equations gives the following. So for the perturbed differential equations, all we're doing is putting x1 plus x1 hat in for x1, and we're doing likewise for x2, u1, and u2. So just as the first step is to make these substitutions. All right. Now notice here, if you take the derivative of this, x1 is a constant. So this just becomes the derivatives of the small signal perturbation, similarly here. And the output equation basically is the steady state value of the output plus a perturbation. And then the arguments of these functions basically involve steady state plus perturbed values. So what we're going to do is we're going to approximate these differential equations. Everything on the right side we're going to approximate in the form of a Taylor series, but only to first order. That means we retain terms involving only first order derivatives. All right, so let's deal with the state space equations first. And so what I've done is expanded out everything in terms of a Taylor series expansion. And since we have basically 1, 2, 3, 4 terms here, that means we're going to end up with 4 partial derivatives terms when we evaluate the derivatives. So you have the steady state value, and then you have the perturbation with respect to u1 times u1 hat, perturbation with respect to u2 times u2 hat, perturbation with respect to x1, x1 hat, perturbation due to x2, x2 hat. You do that for the case of x1 hat and x2 hat. So this one in purple is the operating point. Okay, this term refers to the operating point. The part here that's in pink refers to changes as a result of small changes in u, and in orange, changes as a result of small changes in x. So changes in u and changes in x plus the operating point, basically, this refers to changes in the state variables x1 and n2. It turns out this term will be equal to 0, and so it's only the small signal terms that are relevant here in terms of what you see on the left-hand side. All right, so output equations. We expand this now in terms of a Taylor series expansion. And so again, same idea. What we have is steady state, this equilibrium point value, plus perturbations with respect to u1 and u2, and perturbations with respect to x1, x2. So since there are 1, 2, 3, 4 variables here, that means there will be 4 partial derivatives. So these are the ones referring to changes due to input variable changes, and this referred to changes in the state variable. All right, so let's now look at what this means in graphical form. So imagine you take each one of these individually. So for instance, you want to see how a change in u1 will affect y1, or change in u2 affect y1, or x1, y1, x2, i1, or for y2. So you could take any combination you want. So for instance, if we were dealing with, say, y1 and x1, you'd have y1 along here, and you'd have x1 along here. And what you would be basically just showing is a graph. And that graph basically would have a point on it, which we call our equilibrium point. So the equilibrium point would be whatever that value happens to be. And so if we're doing a perturbation, say, where x in this case is x1, so this would be marked off in terms of units in x1, then what we would do, let's say, is to put a small signal in, and you've shown this as in red. Okay. This basically would be approximation. This would be the first order approximation to this curve, right, at the operating point. And what we want to know is how a small change in x1 influences small changes in y1. And so from here you can see, if we take this straight line, that this maximum point of the input signal, if you basically map it to this line, that would represent the maximum of the output signal, which is here. The minimum point would be over here, and if you basically go up to this black line, move over, this will be the minimum point for the output. And you could then go ahead and also pick all different points along here, and effectively as you trace out the input, you'd be tracing the output. Now you could do that also for x2 and y1, and you could also do u1, y1, u2, y1, u2, y2, u1, y2. So all different combinations you can do, just a simple graph of this nature like this. So this is basically how to visualize what's going on. All right, so now basically what we end up with now is, because these equations are differential equations, but they're linear in the perturbed signals, linear in u1 hat, u2 hat, x1 hat, x2 hat, we can write these out in matrix form again. So if we simplify things, we end up with dx1 hat dt, dx2 dt hat in column form. This is a column vector involving this equilibrium point. This is the partial derivatives with respect to u1 and u2. So this is a Jacobian matrix because they involve partial derivatives, u1 hat, u2 hat, and this is the partial derivatives with respect to the state variables, x1 hat, x2 hat. So everything in purple is b subscript f, and everything in purple in sort of a pinkish color is jf. This is a Jacobian matrix involving state variables, the Jacobian variables involving the input variables. All right, so this is basically the state space equations now in a simplified form. Okay, so output equations, we can do the same thing. We now basically would have a Jacobian matrix for the output involving just the input variables, and a Jacobian matrix for the output involving only the state variables. So they're basically stated here. Again, because these are linear in the input variables and state variables, we can write these equations out in matrix form. All right, so now we can develop the procedure for developing a small signal model. This example is for 2 input, 2 state variable, 2 output. So let's go through the steps. Step 1 is to convert the state variable equations into a state space form and identify input variables, state variables, and output equations. So there are 2 different cases to consider. One is where the set of differential equations and output equations are given. And the second could be, for example, a circuit diagram where the input variables and output variables are given, and you need to determine the differential equation and the output equation. So this involves an extra step until you get basically everything in a form for which you then perform small signal circuit analysis. The next step is to determine the equilibrium state variable operating points. So that would be x1 and x2. It's always the first step. You need to determine what these are, because the only information you're given is the steady state variables for the input. But the state variables are dynamic, so these need to be computed first. Once you have these, and you have the input variables, then you can determine the output variable operating points, y1 and y2. Once you have this information, the next step is to compute the Jacobian matrices, which are for the state space equations and the output equations. And then the last step would be to write out the small signal state space equations and the small signal output equations. And then you can go back to determine what the original equations would be, where x1 would be the equilibrium value plus a perturbation, and x2 similarly, y1 and y2 similarly, as shown here. Okay, so now basically we're coming towards the end. This is the small signal model for the state space equations. Here now we have everything sort of in a compact form. We have this is equal to the DC input term and the small signal term. Now the states variable equilibrium points are established by setting x1, x2, u1 hat, u2 equal to 0. And because there's no change in the state variables, that means the left-hand side is set to 0, which means that these 2 equations are set to 0. This basically, u1's a given, u2 is a given, x1 and x2's are knowns, and so effectively what you're doing is you're solving 2 nonlinear equations with 2 variables, and that should give you a solution. Remember we talked earlier about the fact that you can use a multivariable Newton-Raphson method to solve a problem such as this, the objective being to compute what is x1 and x2. Once you have that, then the problem basically has already been solved. All right, and so once you do this, then this is 0, and so the small signal model only contains those entities which involve small signals. This is not a small signal. You end up with just Jacobian matrix for the state variables, Jacobian matrix for the input variables. And so this is the final small signal states variable equation. And you'll notice here these have to be computed, these elements of the matrix computed at the equilibrium point. So you can see that this term involves x1 equals x capital 1. Well, we didn't know x1 until we had actually solved these equations. Similarly, we didn't know x2 until we had solved these equations. So that more or less basically is the procedure essentially for determining the small signal model. All right, for the output equations, we can do the same thing. Here, again, output equations, you know what x1, x2, u1, u12 are, so you can compute what y1 and y2 are. And the small signal model basically only involves the quantities involving hats. So this is paired with that, this is paired with that, and these two are paired with everything on over here. So this is the Jacobian matrix for the output variables, and this is for the state variables. This is a Jacobian matrix for the input variables. And so these have to be also computed. And once you have that, then you basically have the small signal output equations. All right, so finally, let's look at an example where this is all done. Again, we have to keep it rather simple. And this is something you'll be seeing next term in ECE 231. So this is a transistor. And what I've shown here are the transistor characteristics, which are basically these blue lines you see. And so these blue lines essentially said that the collector current, which is the current flowing through here, is related to the collector emitter voltage, which is across here, based on the current that's flowing in here, according to this graph. So if I put a certain amount of current in here, let's say 220 microamps, then basically this is the relationship I would see between the collector current and the collector emitter voltage as I change the base currents. Also, what I can do is I can write an equation involving the outer loop, and so collector emitter voltage and the voltage drop here and the supply voltage. And so if I write this out, this becomes a linear equation, and that's the line that I see here. So this blue curves relate to the operation of the transistor, and this red line we call the load curve. The operating point is where this load curve intersects one of the characteristic curves for the transistor. So for this example, this intersection point that you see here is Q. This is the operating point. All right, and so that means we're putting 60 microamps in, all right, and we'll get a collector emitter voltage of 12 volts. That's basically the operating point. Now, if we make changes in the base current, right, that means we go from here to here and down to here, then what's going to happen is you're going to be moving up and down this line. And so effectively your collector current will increase or decrease depending on how the base current is changing. So here you have all the information that you need to essentially develop a small signal model. Small changes in the base current causes certain changes in the collector current. All right. Now, why would we do all this sort of stuff? Well, the purpose is to investigate the stability of a physical model about an operating point, which is here, and design a controller that delivers robust regulation, which means fast response without oscillations, and good tracking performance, which means that the error between the requested value and measured value is near zero. So this is a technique that's used very much, particularly in taking a system model, putting into a form that perhaps you can use for designing a controller for the system so that basically everything works in a fashion which is predictable. All right, anyway, that concludes Lecture 8A. Thank you for listening.